Let's look at our notes for 6.1. We're on page 8. So yesterday we learned about using the z-score to find the area. We used the table and we also used the calculator. So we are going to look at today about going the opposite way. If we know the area, we need to find the z-score. And these are all the normal distribution. So mu is 0, sigma is 1. So the first thing you're going to do to find the z-score from a known area is you're going to draw the bell-shaped curve. And then identify approximately where z is. And then you can use the calculator or the table to find z. So whenever you draw your bell-shaped curve, you know that mu is in the middle. That's your mean. So if it says your area is a certain percent, then you know that right here identifies 50%, right? So if it says your area is 0.43, then it's going to be over here. Your z will be over here. If it says your area is 0.75, that's like 75%, so it's more than half. So you just got to pay attention to how much area they're talking about so you know whether your z-score is going to be a positive or a negative, because this would be 1, 2, 3, and so on. And then this is -1, -2, -3. And you know that this area represents 50% or 0.5. Anything below 0.5 would go in the negative direction for your z-score. Anything above would go in the positive direction of your z-score. So you're going to select the closest value in the table, except special cases that are used more often. So we're going to look at our table to see our special cases. So our special cases are down here. This is on the positive side. So look at the positive. Go ahead and close y'all's computers. You don't need them open, so you're not tempted to work on the assignment right now. Let's go through the notes first. So remember, z-score is here for your tenths place, for ones and tenths, and then here's your hundredths. Everything inside here represents area. So see how your positive score, see how this is 0.5, which is 50% or higher? On the negative side, this is 0% all the way up to 0.4641. So it's increasing as you go through the body of the table. So our significant ones are common ones, like 1.64 represents 95% of the area. So this would be 1.645 is 0.95. Let's do 00, because we're going to 4 decimal places. So this would be to the far right. So if you think about it like this, here's your mu at 0. And then you have 1, 2, and then behind it is -1, -2. So if we're saying 1.645, that's like right here, a little bit above 1.5. So it's saying that this area right there represents 95%, 0.95. That's what that's saying. So then we also want to know at negative 1.645. So that would be over here, negative 1.645. I didn't write the number there. But this is another special case. See how these are opposites of each other? You have the positive 1.645 and the negative 1.645. Added together, they'll equal 1. So what this one is you do 1 minus 0.95, or we could look at our table. I'm looking at the negative z-scores. It's 0.05, 5%. 5%, 95%, make 100%. So this is 0.500. So together, well, these are complements. Y'all remember that word complement? You do one minus the other. So if you have the positive of the same number and the negative, they're complements to each other on the area. So they add up to equal 1. And then the other one, let's do 2.575. So that's really far over here. And what that represents, this is on the positive side, 0.995. 99.5% is the probability. So 0.9950. And so the complement to that, if we subtract it, is 0.005, which it shows you on this table too, 0.005. And then anything above 3.49, so think about how small that area, or below negative 3.5, that is, let's see, 0.9999 for above, because that's almost the whole curve there. So then anything below is, I should put a 0 there, 0.0001. Super duper small because it's from this point on. Well, actually it's 3.5, so it's like here. It's a very, very tiny sliver of that curve. So let's look at the example. It says use the same thermometers as before with temperature readings at freezing point of water that are normally distributed at a mean of 0, standard deviation of 1. So that's our normal symmetrical distribution. Find the corresponding, or temperature corresponding to P95, the 95th percentile. Find the temperature separating the bottom 95 to the top 5. So whenever I say P95, this means that the area or the probability is 0.9500. That's what the area is, and it tells us that right here. So the area under the curve is 95%, or 0.95. So we are going to, we could first look at our special cases. This actually falls in the special cases. 1.645 is my z-score. So we search for the area of 0.95 in the table and then corresponding z-score. This is in the special cases. So we're going to say 1.645. So it's 1.645 units above the mean. So the 95th percentile is a temperature reading of 1.645. When tested at freezing, 95% of the readings will be less than or equal to 1.645. So P or Z is less than or equal to 1.645 equals 0.95. That's how it'd be written. let's look at the next page. Example 1B, find the temperature separating the bottom 2.5% and the top 2.5%. Okay, so the area, see how the area, it says 0.0025. So we know that this is going to be a negative z-score. So we're going to look on our negative z-scores, and we're going to look in the body of our table for 0.0025. Have you found it yet? 0.0025. So it's right here. So it's at negative 2.81. See how this comes out to negative 2.8 and then come down here and that's a 1. So negative 2.81, right? Did I find the right one? Nope. What's wrong with that one?
It's 0.25.
Yeah, I looked for 0.0025. That's a common mistake. Where would the other one be? Okay. There we go. Negative 1.96. So it's actually right there. So negative 1.96. So don't pull a Missy Saucy and get that one wrong. Pay attention to those. If it had that extra 0, maybe I would have caught it. I don't know. All right, so then the other one is find the z-score to the right for an area of 0.957. These are complements of each other, right? They're symmetrical. This one's at the negative z, and this is at the positive z. So this one should be positive 1.96, but let's check it. So let's look for 0.9750. 0.9750. And there it is. Oh, hold on. There we go. Positive 1.96. So this z-score separates the bottom 2.5% from the top 2.5%. The values 1.96, well, positive, negative. I'm going to put that positive, negative symbol. Separate the bottom 2.5% and the top 2.5%. So together, these 95% of all readings. So if I take 0.95, 95% minus, I did the same thing here, didn't I? Didn't even notice that. I take away the 0.025 twice of them, 2 of them. Do I want to take it away or add it to get 1? I actually want to add it. That should equal 1. So 95% is in the middle, 0.95. And then you have the lower 2.5%, because I would move this over 1, 2, 2.5%. So the bottom 2.5% with the top 2.5% added with 95%. So they fall between positive 1.96 and negative 1.96. Okay, use the previous example about bone density tests that are normally distributed with a mean of 0 and a standard deviation of 1, so they meet their requirements for standard normal distribution. Find the bone density score corresponding to P90, the 90th percentile. That is, find the bone density score that separates the bottom 90 from the top 10. So go ahead and make your normal distribution. So you know mu is in the middle, 0. It's saying the top 90, so that's there, and the bottom, well, top not 10% in the bottom 90. So we actually just want this. We don't even want this. We just want this score right here. We want to know what that z-score is. So this is representing 90% of the area. So we need to find 90. And so this would be in the positive z-score. So we want 0.9. Is there a 0.9 in the body of our table? Let's see, 0.9. It's kind of between here, right? 0.8997 and 0.9015. Actually, if we look down here, there's some critical values. We can use this. Confidence level, which will be our area, 90%, is 1.645. So we can use that one as well. So Z is 1.645. Which it's going to say P90 equals what? It equals 1.645. Okay, we are going to skip this example and use a different one. I'm going to draw a normal distribution, and we're going to find the Z. So it looks like that, where the area is 0.1469. Okay, the only thing that this one is different from the others and from the table is this says area from the left. I could use this and get a negative z-score and make it positive, or I could go ahead and subtract because I actually want to find out what this area is so I can find my z, because that's what the table uses. So I actually want to do 1 minus 0.1469. 0.8531. So that is the area I actually want. So it's a complement. So let's find this in the body of our table. 0.8531. So it's going to be on the positive side because it's over here. It's bigger than 50%. So 0.8531. So look in the body. See if you can find it. 1.05. So we'd say Z equals 1.05. Okay, we're going to do one more like that. This time it's going to be on the negative side. And that's what we're given. And they're going to say that this area is 0.1762. So we already have the area to the left, so we need to look at the negative. So I want to look for 0.1762. 0.1762. Y'all look for it.
So
Negative 0.9 what? 3. Yep. So Z is negative 0.93. Okay, cool. Okay, critical value from a standard norm distribution, a z-score separating unlikely values from those that are likely to occur. Z alpha, where A is our Greek letter, so it's like this, kind of looks like a fish. Is the way you'll see it. So it's with the area to its right. So this is different from the area to the left. But you can still use the table by doing 1 minus alpha. So this would be Z alpha. And it's talking about the area to the right. So you would just need to subtract from 1 and then find your value in the body of that table. Finding critical values will become extremely important in the next few chapters. So if we have this example, it says Z alpha, let alpha equal 0.025. Find the value of Z alpha 0.025. So we would look at it with our value here. So if it's a really small value, but we're saying alpha is 0.025, then it's the area to the right. So it's going to be really small, 0.025. So we want to know what Z alpha is. So this is actually in our critical values, the common ones, I think. 0.025, maybe. Oh no, let's look at the table. So it'd be area to the right. It's not. So we need to look at the table. So it'd be we need to subtract, right? So let's do 1 minus 0.025. So this represents 0.975. So let's go to the positive z-scores and look for 0.975. So we're on the positive side. So it's right here, 1.96. So Z of 0.025 equals 1. What is it? 96? Yeah. All right, there is another way to do it. I'm going to show you in the calculator. We're going to skip that one. In the calculator, we're going to do second vars. And go to inverse normal, number 3. Push enter. The area, so the area for the last one, you want to always do the area to the left. So that'd be 0.975. So I'll put that area, use area to the left. And right now, our mean and our standard deviation are the same. So then, paste. And this gives the exact 1.95996, blah, blah, blah. Our table, it rounds for us to 4 decimal places. So you can use the table or you can use the calculator. Just make sure you pay attention to what it's asking you to round up to. All right. One other thing that I saw on y'all's homework is if we have P3, that's going to mean we have 3 and we want to move the 3%. You want to move that decimal over 1, 2. So it's 0.3. So the area is going to be 0.03. There we go. So if we have a graph, this is 50%. Where is 0.03 going to be? It's going to be over here, right? So we could say this 0.03 is our area, and we can use the calculator for that. Use the inverse norm. So second bars, inverse norm, 0.03. And our z-score is negative 1.88. All right, so that is all I have for 6.1.